You are now relearning economics.
Welcome back to the live stream. If you're having trouble hearing me on the mic, let me know in the chat so I can adjust it on the fly. We've got people here today. We've got Mike Radzicki. He's back on the show. Don't know where he's been. We'll ask him, see what he's been up to. Steve Keynes is here, the great heterodox economists. And we've got a very special guest, and I'll introduce him momentarily. But first, let's bring up Mike. Let's do Mike first. Mike.
Yeah.
What's been going on?
Well, I don't know, sort of the same stuff, working in my barn and doing economics and just paddling furiously to keep my nose above the waterline.
Okay. Yeah, we've moved the show to my channel, so we've gone from hero to zero at this point, so we're starting from scratch. I've changed the name. I've done a play on my name, so it's now the Mr. Keynes and Dr. Keen, the live stream, the economic live stream. I'm still not sure. I'm still working it out. Now, we could put you in there, right? We could put you in the title somehow. I don't know how we'll work it out. Radzicki.
I'm not good at those marketing things, so I don't know.
Neither am I. That's why we're trying to figure it out live instead of in private and deep think tank meetings
in real time. Yeah. Okay.
Yeah. Anyways, anybody's got questions in the chat, make sure you put them in the chat. If you're on X, you can put them in the chat there. If you're on YouTube, you can put them in the chat there. If you're on my Patreon, patreon.com/relearningeconomics, you can't put questions there. You'll actually have to come to the YouTube chat and ask your questions there. I will bring on Professor Steve Keen. Steve.
Hey, guys. Hey,
Dave.
How you doing?
Fine. I'm going to fill in part of Mike's background, because he forgot to tell us he's trying to revive the economics wing of the system dynamics special interest group. So tell us about that, Mike.
Yeah, well, actually, we had a visitor from Turkey, the country of Turkey.
Oh, yeah.
And he asked why, aren't we doing stuff with the special interest group, economic special interest group of the System Dynamics Society? And I said, I don't know. You need a champion for any of these things, someone to herd the cats and line up speakers and, all that stuff. And I said, I currently didn't have the bandwidth. But I said, if you would like to do it, and he said he did, if I would help him. So I said, all right, I'll make the initial, requests for folks to gather and what have you. And so he's taking over, and I'm still helping. And he has more energy than me for this. He's younger than me. So
tell me about it. Yeah.
So we'll see how that goes. The current working idea is we'll meet once a month online and have a speaker, paper, whatever.
I think I'm your first speaker, aren't I?
Probably.
Yeah, that's my reason. Self-promotion here, talking about marketing.
Yeah, right. And we'll get Ty in there, I suppose, and then just we're working towards maybe once a year gathering and for a face-to-face annual thing, and maybe with other economists. I don't know, maybe not with other economists. Hard to say. Again, I'm just a helper now, so we'll see what unfolds.
Nice stuff. So today we're gonna do a little bit of agent-based modeling, talking today. We usually talk about system dynamics mostly, and I want to kind of nuance this. We all like agent or system dynamic modeling because of its emergent properties in a system. It's very interesting, right? So if you got a mental model and you formalize it with some math, you can find some really, cool things that happen if you like looking at plots and squiggly lines, right? And comparing it to reality. And we've, the three of us are always trying to push that to be used in economics more. But there is another modeling technique out there, and it's agent-based modeling. We got a guest today that has taken that to the extreme. His name is Aish Chopra. I got his name right. So he's going to come on. He's going to talk about agent-based modeling, but not just any normal agent-based modeling. Agent-based modeling on steroids. Here he is, buddy. I don't have claps
Hi.
anymore. Here you are.
Hi, nice to meet you. Hi, how are you doing?
Hello, hello.
Okay.
All right.
Hi, yeah.
First and foremost, who are you? Tell us a little bit about your background and how you kind of came into agent-based modeling and, of course, the extension you've added to it.
Okay, hi. I'm Ayush. I'm doing my PhD at MIT. I'm at the MIT Media Lab, and I've been doing like agent-based modeling for the last 5 years. So when I first got into it, like agents were not really as hypey a thing, but these days, like a lot of people are interested in. So it's good to know that after many years, people sort of seem to care about what I'm working on. But I came from like a slightly non-conventional background. So I used to work for Adobe beforehand. So I used to work on like a lot of computer graphics and just imaging problems. And the group I came to at MIT was called Camera Culture. So it's a group that builds cameras. So a lot of our research was focused on simulating photons. That we simulate light to build cameras. They can sort of look around corners, see through fog, or cameras that learn to not see a part of the world. So we used to basically do a lot of like simulations of photons. And then the pandemic happened, and we sort of realized a lot of the ideas that we built to make light simulations more effective, because they're super fast. They simulate like millions of photons to render a pretty scene. And you see it all the time when you're watching like an animated movie and like the princess moves up in Frozen and you'll see like this reflection on the bottom. Or you'll see like some source of light move, or like the scene becomes dark or bright. Like millions of photons are being simulated to make it happen. And over the last 5 years, we spent a lot of time trying to bring a lot of those ideas to go from simulating photons to, in some sense, like simulating people where there are like millions of interactions. And that's sort of the direction we came at it from. And we sort of use it for applications in urban science to help like people figure out like how to basically, where should there be bike lanes in a city, or we use it to figure out like how might diseases be spreading for like a lot of epidemiology applications, which has been like the bread and butter for a lot of like these agent-based models in that sense. Where like, and increasingly we're starting to do a bunch of like more supply chains, infrastructure, a little bit of like labor markets work in like one of our more recent projects, but that's sort of where I'm coming at the problem from.
That's quite fascinating. So you actually began from simulating light for artificial photographs fundamentally, and you have millions of photons simulated. Yeah. How many photons per second?
I mean, so it's like photons per second isn't usually like a very good proxy, because like the whole thing, like photons sort of move in like continuous time. The difference between the photon problem and the agent-based problem is just two things. That with photons, we have something called the light transport model, which just describes how do photons move in continuous time, so that they hit through the world and they get to an end. So there is not as much spatial structure because you don't look at like photon interactions. Yeah. But to be able to render one frame, you'll probably look at like millions of photons, because you have this continuous time process and you have to like integrate it, and you end up like just adding like millions of rollouts to get a good answer. But to be able to see one frame, create one scene, you'll do like millions of photons. And to create a video, you need to see things at least 16 frames per second.
That's right.
That's when you start to feel that, it's more of a video-like. So you can imagine like several millions of like photons with a lot of interventions in the system, because you interact with the environment, light gets reflected, it gets refracted. There are some interventions like, here is a light source, here is a camera, here is a sensor, like bunch of things keep happening.
So let's sorry, Mike, what were you going to say?
I was going to say that this should resonate with Steve, as his buddy William Nordhaus has a famous paper that he uses lumens of light to measure technological process over time. So
that's about the only
econ and light are.
That's actually, I've got to admit, that's about the only paper of his that I haven't read, and it's probably the only paper he hasn't got something coming out his ass. So that might be worth having a moderate look at. But everything else is done.
It's a clever paper.
Sorry?
It's a clever paper.
Is it? Okay. Unlike the rest of his garbage. Fair enough. Okay.
Strong endorsement for Nordhaus right off the top of the bat of the show. Now, Ayush, tell me, tell me like I'm a 6-year-old child. What is agent-based modeling? What are these agents? Do they interact? Do they have rules? Kind of explain the basics for me, like I'm a child, so I understand it.
Yeah, so agent-based modeling is just like a way to like model a process. So like the core unit, so agent-based modeling usually have, like I'll give you an example, like, and I'll give you like a very simple problem, like why it matters. Like imagine there's like a disease like COVID that's spreading out in the environment, and the government says like, oh, you have to take a test. And based on the kind of test you take, like, and the question they care about figuring out is what kind of a test should people take? So they come to you and ask a simple question that an infection is spreading, you have to take a test to detect it, and you have two choices. There's something like a red pill in some sense, which says that, oh, here is a test that has only a 10% false positive rate, but will give you a result in 3 days. And then there is test 2, which has maybe a 60% false positive rate, but will give you a result in 10 minutes. So there's like the red pill and the blue pill, and they come to you and ask, like, as an individual, given who you are, which of the two tests do you want? Like, what do you pick? Like, you've got, and both of them have the same false, like there is no false negative. So both of them will, if there is an infection, both of them will detect it. The only difference is a false positive rate.
So are the decisions in agent-based modeling, are they based on some sort of distribution, a random number generator, or are they completely rules-based?
So it depends. So like, for example, to like answer this question, like for instance, just like take a shot. Like if you were to answer this question, what would you pick? Like if I just asked you this question, like, do you want the test with like 10% false positive rate that takes 3 days, or a test with 40% false positive rate that takes 1 day?
Yeah. I'd probably go for the, if I was feeling crook, I'd go for the 10-minute one. And but yeah, so the agents, do they make is there a stochastic element to the?
Yes.
Okay.
Exactly. So for example, to answer these questions, like you need to like, what you're trying to say is that each agent, for instance, if as a city government, if I'm trying to figure out, I've got 5 million people in my city, what kind of a test should each person get?
Yeah.
The way they'll do it is like they'll basically create like a system with like 5 million agents. Maybe you think of each citizen as an agent. You try to figure out the process. There's some state to an agent. Their state is like, let's say, what is their age? What is their geography? What is their occupation? What is this demographics? Like, what are their comorbidities? Anything that makes them susceptible to an infection or may influence their behavior or response to some intervention you put on them.
Yeah.
So you define like, let's say 5 million of these agents. And then the next thing you do is you try to simulate the process of how infection spreads. You try to look at like, how does each individual in the population interact with other people? What happens when they interact? How does this disease spread? What does it depend on? So you try to basically model the system dynamics of the disease, but instead of running it on one average person in the population, you try to run it for each individual in the population. And you basically describe this kind of a simulation. And then what you simulate out is that each step of the simulation, these agent-based models are generally discrete time. Like they have a component of time, but it's chopped into like discrete time intervals. Yeah. So you might be like, I want to look at how will this disease play out in the next 45 days. And one time step is like 1 day. So at every step in the simulation, every day in the simulation, all of the people can move around. They interact with a bunch of other agents, which are like citizens as agents in the simulation. They spread infections. As a result of infection spread, their state may change. Infected people then go and infect other people. So the interactions are very stochastic, because if two people meet, they may or may not get infected. If a person sort of gets infected, they may or may not test positive. If they test positive and there is an intervention saying quarantine, they may or may not quarantine. So these systems are very stochastic. And there is these like, so interactions happen at multiple time scales. So if I get infected today, I may show symptoms in 5 days and start to infect people in 3 days. So a lot of like multi-scale, multi-time, in terms of space, in terms of time, a lot of these complex interactions start to play out in the system. And agent-based modeling sort of is like the computational technique that allows you to simulate out these systems so that you can then measure the system at the level of an individual. You can measure it at the level of a group of 10 people or the entire population. And that's sort of the way people study this problem, because a lot of the insights and arguments are that the decisions you get when you look at a system at an individual level, the emergent phenomena can be very different depending on the scale at which you study a system. So for instance, in the test example that I was telling you, if I'm an individual thinking in isolation, a lot of people might actually take the slower test, which is more accurate in terms of like a lower false positive rate. Because if I'm infected, I want to know. If I'm not, I would much rather not quarantine at home. But when you think in terms of the entire system and how you getting infected today can, like how infection spreads through interactions, and if you miss out people who are infected, then there's possible for like viruses to mutate, people to go out and spread infections to other people. They'll realize that, oh, thinking in terms of a longer time scale, the decision that like Dr. Keynes said, that I want to take the faster test will actually be more optimal. So what you'll realize is that even individual decisions and preferences can change based on like how far out in terms of space and time you look at the system. So agent-based modeling is just like a computational tool that allows you to study these kinds of systems, where there are like millions of interacting entities, and scale in terms of the number of people, number of interactions significantly affects the emergent outputs.
Yeah, Mike, I was actually going to ask you next, kind of nuance that with your experience with system dynamics, and anything you were thinking about saying too, you're free to say.
Yeah, the first thing I was going to say, there's a well-known paper by John Sturman and Hajir Ramadad that directly looks at a system dynamics model and an agent-based model of an epidemic, and under what circumstances are the models yielding the same results, and when do they differ. And a lot of times they give you similar results, and other times the agent-based model, when the heterogeneous agent characteristics really matter, does a better job, for example, but at a cost. It's more time-consuming and detailed work to produce the ABM model. So it's kind of different tools in the toolbox for depending on what you're asking and what have you. And when I would teach ABM, I was taught like in summer school with Yuri Walensky and Bill Rand with the NetLogo. So media lab there. Shout out to the media lab. You know, that we would build models that SD, and because you can do SD models as well as agent-based models in NetLogo as well as in AnyLogic, and we could show side by side the SD and the ABM running side by side, generating the same results. But then the more complicated the heterogeneous characteristics became, the more the SD model was clunky to use. It was much easier to do it in agent-based modeling. But there's other, if you bear with me just a second, there's other differences. It's just, they're sister techniques. They're both excellent techniques, and it shouldn't be one or the other. You know, really a simulation scientist should have both, including discrete event modeling for that matter, in their toolkit, and you pick the right tool for the right job. But, you know, in system dynamics, we start with a reference mode. Here's a picture of the problem, the aggregate behavior. It's a top-down approach. And of course, ABM modelers like to see emergent behavior. You give the agents very simple rules. Either humans are using very simple heuristics, or nature gives, you know, Newton's laws or whatever to the, and the aggregate behavior emerges. And it's not emergent if you know by looking at the individual rules of the agents what the aggregate behavior will be. Well, it's just the opposite SD. You start by knowing what the aggregate behavior is. So in some sense, they are sister techniques. They have feedback, they're dynamic and all that, but they kind of start from different places. And they're both brilliant tools properly used. And yes, occasionally they can give you the same results.
So we've got a question. We'll get back to Ayesh's like larger model here and what he's working on, but maybe this is a good one for Mike. And you could nuance, what sort of insight can agent-based modeling provide in terms of economic phenomenon? For example, how spending habits might be impacted by interest rate changes. Mike, just like hearing that question, you know, how would you respond to it? You know, what are the nuances you can get out of agent-based modeling?
So it all depends on exactly what question you're asking. So let's say we're wondering about a population, and you say, well, there's a stock of people, okay, and we don't care if they're young, old, rich, poor, whatever, and then we're just counting people. But then you say, well, we want to make it draw a distinction between males and females because population growth, you have to have both. I'm told in biology class and whatever, right? So now we have two stocks of males and females. But wait a minute, you only have babies when you're younger. The really old people don't. So now we need age groups. But wait, among the age groups, there's rich people, poor people, middle income people. But wait, they're highly educated, sort of. At some point, you're throwing up your hands and saying it's an ABI. To try and do that with a system dynamics tool is just gets crazy. The question becomes, for an interest rate change, does that stuff matter? Does your educational level matter? Mm-hmm. Does your income level matter? And what have you? And depending on how many of the heterodox characteristics of the agent matter and how many of the folks there are in each category, it might be an ABM problem. And final point here, in our system dynamics program with doctoral students who are really interested in system dynamics, they're using it to do a PhD, to try and get them to say to themselves, not every problem is a system dynamics problem. You got to tap the brakes a little bit and don't try and necessarily jam the square peg into the round hole. It might be a discrete event problem. For that matter, it might be a regression problem or a linear programming problem. You got to, be armed with a toolkit, and you might not be an expert in 15 different tools, but at least you know enough to know, hey, this is really not an SD problem or ABM, whatever, and pick the right tool for the right situation.
Right. Great answer. So essentially, I got one more. Before I go back to Aisha's larger project he's working on, brought up the wrong one. Here we go. This one's for me. So I did use regression to kind of prove, the structure of the system that's what we were seeing. So I take a single input. So his question, are you using regression analysis to refine your model and tuning parameters? I did to prove like theoretical concepts of the model, but we've since turned it over. And this week, we've finally done a full integration where we have a machine learning algorithm that is changing the system's parameters based on empirical data, high frequency data. So that's how we're doing it now. And Doug is actually handling that end. Machine learning, I'm not afraid to admit there are some skill sets I don't have. So I don't have a really good skill set in machine learning. I play around on any logic with agent-based modeling, and I'd really like to create a hybrid agent-based system dynamic model one day where I'm focusing on single sectors and using agent-based modeling and then tying that into a large macroeconomy system dynamic model. One day I want to do that, but there are things that I don't know. But yes, I use regression to kind of prove, that the structure of my system behaved the way we saw it in the real world, to answer your question. Aish, tell me about this. Now, you were telling me before the show, you have 350 million agents in a large population model. What the hell is that? That sounds revolutionary. I'm thinking I might need you in modern macro technologies to build out a basic simulation for the stock market. Tell me more.
Okay, yeah. So I'll give you some more context. So I'll build on top of the previous question. So when they were describing the problems in which agent-based modeling especially helps, there are problems where you want to describe a lot about an individual. So there is a lot of information about each of them, but you also care about how they interact with each other. For instance, one of the problems we care about right now is the US labor market. There are millions of people who work in the economy, and we've got a lot of these new automation tools that can start to do some of the jobs that humans care about, or things that humans have conventionally done well. So what we started to do was we were let us build a digital simulation of this entire labor market, which includes around 171 million agents that are working and 330 million people across the entire structure, which includes people in households, non-working, people who choose to not work, elderly people, children, to have a simulated version of a digital population that mimics in terms of structure and similarity a real population in the world, which is the United States population. And what we start to simulate is we describe each of these agents with a lot of information. Using the information that we have in the census on the BLS, we try to describe what can each agent do? Like, what are their skills? What are their job descriptions? What are their tasks? Which zip code they live in? Or like, what kind of, how much money they make? What's the local environment? What is their education level? So based on information from the census, which is public information, we build very rich descriptions of each person. So each person's state now is like a lot of numerical information, which is like their job description, which is like their income level, age, demographics. We also have a lot of like textual information, things about like their task descriptions, job descriptions, interests, capabilities, everything the way the census describes a person's job. And then we look at interaction structures, like what kind of an environment they live in, which zip code they live in, what's the housing structure there, what kind of people they seem to work in, what's a plausible distribution of their household structure. So we create like this kind of a digital similar of like a population first. And then we start to, we do this for the human population. And we already have like a lot of census information for us to build this. And we've built these tools called large population models that allow us to simulate this complex population super efficiently. Like Mike mentioned, that these things can sometimes be computationally efficient. So we built a lot of new algorithms that allow me to simulate the scale super fast. For instance, our algorithms do like 300,000 interactions in 1 second, or they'll do like 1 million agents on a single GPU, so that you can simulate out this entire computation super fast. But this allows me to capture the human population. So what we also started to do is like we then started to build some kind of like a census for AI. Like, what can AI do? Like, that's not like, because agents will start to do human usable work. So we sort of extend this population with like all the AI agents and all these tools that are emerging. And then we map them back to the set of skills that the US Census Bureau cares about. Like, here is a list of capabilities on like, what does a job look like? So then we basically try to simulate out like not only how humans interact with each other in the physical world based on geolocation, industry, capabilities, but we couple this simulation with like how might human workers interact with like a potential population of AI workers across similarities of skills. So this sort of points to like this kind. So most of these large population models that we build are like these millions of agents that interact with each other, influence each other, and interactions happen at all time scales. So it's like a more sophisticated version of an agent-based model in the sense that it has a lot of discrete time interactions, but it also has discrete event interactions. Because for instance, I want to simulate out like, what if you give people a stimulus check? So you might give them stimulus money on infrequently, like 2 to 3 times a year. But you want to simulate like, how are people going to work on a daily or a weekly basis? Or what's happening to like the labor market every quarter? Things like that. Or you're trying to basically measure what kind of skills can agents do. So that becomes like a system dynamics problem, because a lot of the AI agents and their skills may not necessarily have the spatial and the temporal structure to be modeled as an agent-based model. So we build these complex system simulations, which have discrete time, discrete event, continuous time, system dynamics, and a lot of these complex behaviors so that you can simulate out different kinds of emergent effects. For instance, one of the emergent effects we try to simulate out is that can we predict like what proportion of jobs can be automated can be augmented with AI? What percentage of jobs can be automated with a lot of the automation tools that are being built? So, and then you can optimize these simulations in themselves only. For instance, so this project we call Iceberg, because our hypothesis is that a lot of the jobs that you feel can obviously be automated, a lot of the general purpose mean field models can build. But there's a huge segment of jobs that can benefit from AI, which are sort of hidden underneath the surface, like how an iceberg has like a small percentage on top, but a major chunk underneath the surface. So we are able to sort of, our goal is like, how can we make these hidden effects visible? So we do that by building a very bottom-up simulation of the entire labor market in some sense, and then starting to put intervention in the system. You ask questions that, oh, what if I invest in AI capabilities for this kind of a job? Or what if I have AI tools that are better at these kinds of tasks? For instance, if AI becomes at writing code, you want to see how will it ripple out across finance and consulting and marketing and software sales. Or you might care about questions like, how will it change multiplier effects in the economy? For instance, like historically, like what we learned from a lot of like economics people that we've had conversations with was like, jobs tend to have multiplier effects. For instance, if you had like one job in And like if you had one construction job, that would end up creating 3 or 4 jobs in adjacent industries. But what happens now with AI is that maybe some of those jobs were accounting jobs or like data management jobs or just marketing jobs, which may potentially even be automated by AI. So this multiplier effect of the number of jobs that get created from each investment will change. In some cases, it can go up, go down, but in a lot of cases, it will start to go up. For instance, investments in nuclear energy can now start to create significantly more number of jobs rippled out across different zip codes, districts, economies than they would have conventionally done. So this is sort of the kinds of problems we are trying to simulate now. And to do this, the computational tool we have is this concept of a large population model, where like systems that can simulate millions of interacting entities. These entities can be individuals in a specific jobs. These can be like AI agents that can do some kind of work autonomously. These can be zip codes, and you have these a lot of these heterogeneous interactions. And primarily to understand like primarily to be able to measure like how AI could transform the labor market.
Steve,
So, sorry.
no,
Yeah, I'm just-
go. Yeah, okay. Steve, you go first, and then Mike.
Okay. What I'm wondering about, obviously, we're interested in economics here. Macroeconomics is our thing, and the role of finance and money in macroeconomics in particular. So how do you go about modeling that? And one issue which I have, and this you might have a solution for this, is that most of our data on macroeconomics is actually aggregate data. We don't get information about what individual agents do. We get the collective outcome. It's very bad data, I might say. We've just seen some numbers come out today that totally revised the change in employment data from last month. So what was like supposed to be 140,000 new jobs actually turned out to be 17,000 new jobs. So you really can't rely on the data. But nonetheless, a lot of what we see at the macro level is a result of emergent properties that come out of the individual level where we don't have the data on the individuals. So how do you go about designing individuals that give you macroeconomic outcomes that capture those same emergent properties when you don't actually, well, maybe you do, but I'm wondering how do you do it for data at the micro level? Because certainly from our experience, we don't have that micro data.
Yeah, so basically, this is where this is sort of one of the problems we were trying to solve with like large population models, is that what's the diversity of data that you can work with? For instance, when describing individual agents in the population, we have models that can describe, like we can have millions of entities, but you can, for instance, use like language models to describe each of the interacting agents, or you can look at many different kinds of interaction structures in the graph. So to set up the simulation, a lot of the capabilities and interactions that we look at come from more of like natural language descriptions. For instance, we are not using as much of like labor data because we are not trying to calibrate or predict unemployment rates. We are trying to look at more qualitative capabilities from the standpoint of like, what can you potentially do? Not in terms of like, will it happen in the next month or the next 2 months? So a lot of the data that we end up using is like textual descriptions, which the BLS measures about like, what does it mean to work in a specific kind of an occupation? So basically, for instance, the way the US, like sort of Bureau of Labor Statistics seems to look at the employment problem is, we found that they break down the entire economy into 923 jobs. They come from 23 different major groups, around 200 minor groups. And each job has like a combination of skills, capabilities, task descriptions. And through our systems, when you process them, you come at like an entire span of like 32,000 different skills and capabilities. So that's the all kind of the span of what you can do. So our state space is actually 923 jobs, 32,000 skills, and 170 million workers in some sense. For each of those jobs and skills, there is a lot of natural language description, categorical description, numerical descriptions. Based on that, we are able to basically, by looking at similarity between jobs, through our simulations, we're able to predict like job-to-job similarity graphs. For instance, what's the similarity between a physician assistant and a legal assistant? They may come from very different industry codes, they may come from different parts of the labor market, but there are some parts to their jobs that can overlap, or like some parts to their skills that can overlap. For instance, like a welder and a robotic technician in some states have a lot of like overlapping skills. based on education, the tasks they do on a daily basis, kinds of tools they work with, the kind of personality and interests they seem to have. So the Bureau of Labor Statistics provides a lot of these detailed descriptions. So like when we are setting up our simulations, we use basically like our models have the ability to have like to basically put all of this multi-modality data together in terms of text descriptions, interaction graphs, numerical attributes.
Okay, just for a moment, Athav, please stop spamming. I will respond to you later. Okay, I've seen the message. You've put it there half a dozen times. Please don't do that. Sorry, this is one person in the audience who continues pumping the same question 15 times in a presentation. Ty, just take a note of that one, and we'll talk to him later. Okay? Yeah. So that's what I'm fascinated by here is what are you coding? What language are you coding in? What is the computing structure to enable those interactions to occur?
Yeah, so basically to build these general class of models, we call them large population models. Like this is one of the applications, and to make them happen, we built our own framework. So the framework is called Agent Torch. So a lot of the standard works in machine learning happened with this framework called PyTorch, which has allowed you to build these large-scale neural network models, and a lot of the LLMs have been built on top of PyTorch. So to basically make large-scale agent-based modeling happen, but building on top of a lot of the tools that machine learning has given in the last 10 years, we built this new framework called Agent Torch. It is written in Python code. It's like very simple to use. You can get started in 3-4 lines of code. I mean, it's just GitHub/Agent Torch/Agent Torch. It's completely open source. We maintain it, and like with very simple lines of code, like you can just write 5 or 6 lines of code, and it'll allow you to simulate the same model on like a population of 100 agents. And just by changing one line of code, you can go from like 100 agents to a real population of 1 million agents. And it gives you like all the performance efficiencies on like how to basically compile programs on GPUs fast. It runs on CPUs, it runs on GPUs. It has you can write the same code, run it on 100 GPUs in parallel. You can run it on 1 GPU. But it's a very simple Python code, like how you might write like, for example, in Mesa, like a lot of people used to use Mesa for agent-based modeling a while ago. You need to write equal kind of like simple Python code, but it just abstracts away all the technical complexities of making sure the simulations run fast, or how we sort of work with the underlying hardware, or how we allow the simulations to ingest data. Because our simulations also have a lot of other algorithms that allow them to integrate a lot of this multimodal data, or you can calibrate them super fast. Or for instance, in our simulations, sensitivity analysis are free. You never have to run a simulation to do that. So we give like all those abstractions to do that under the hood, but like what you have to use is just very simple lines of Python code.
Okay. So if you push my luck a bit here with a couple more questions, can you show us a sample of some of the code, and how do you visualize this when you actually see the results of a model? How is it visualized? So if you can share a screen to show what you're talking about, that'd be really informative.
Yeah, for sure. Oh, where do I?
It's if you look, put this thing in, put it in exit full screen, and you'll see down the bottom there's a share screen, which is the letter H apparently. There you go.
Did you see my screen?
Yeah, we just started seeing it then. So try it again.
Yes.
I got it.
Here we go.
Just hold on.
Our boss has got it. Yep.
Yeah. So this is the framework. It's called Agent Torch. It's right here on GitHub, and it's very easy to start. For instance, to be able to run a simulation, like you just have to do these 3 lines of code. Like, for instance, we give a lot of example models. So we have like a lot of documentation on getting started here. It walks you through like what are the capabilities. To install the framework, you just have to call this 1 line of code. It's very simple, like Python installation, just call 1 line of code. To be able to write a model, these are sort of all the lines you need to write. So for instance, we have a lot of these standard models that are already pre-built. For example, we have like a disease model that you can run on an arbitrarily large population. So to be able to run this model, you just like import a couple of things, and then you just literally just create a simulation object by just specifying the model, specifying the population, and you just initialize the simulation and you just execute it. Okay. So you just call. So when you call these 5 lines of code, it ran an entire simulation on like 40,000 number of agents in like Astoria, part of New York City, trying to simulate how disease outbreaks happen. But you can take the same code to like go on even larger populations. And yeah, we give a lot of like very detailed tutorials on like how to create a model. We have tutorials on like how to like describe it in like Python code. Like if you want to build your own new model, again, like that's also, this is like all the code you need to write to build a model.
So you've got a database of human characteristics there, but you're storing it like the data. I'm an ex-database guy. I used to design databases, so I'm used to using programs like Advanced Revelation or PIC databases or entity relationship models and so on. And you actually have an entire defined data structure. You're doing this in the Python code by the looks of it. So if you, how would you see it? How would you see the definition of an individual entity with all the characteristics you put into one of those models? How would you see that in the code itself?
Oh yeah, so basically like we have like our own model concept. It's called an agent. So basically we have a lot of these builders. To build an agent, you just create an object called I want to build an agent. These are citizens.
Yeah.
So each citizen has a property, let's say just a position. Right now, like we built a very simple model in which these citizens move around in a 2D space. They jump around, they do X, they do Y, something like that. So each citizen, for instance, here just had one property. Like you just get to move around in 2D space. So you just have to say, what's the name of the property? What's a random value you want to initialize it to? And you just do that. And when you do this, you just say that I created an agent. I created this property called position and I added it to the agent. When you do this internally, it creates like a huge matrix, which could have like, let's say you created this with like million agents. So initially, internally, it will create a matrix of like million by 2 to track like the position of all of the individuals in the entire population.
Okay.
You can do that. For instance, if you want to do something like, oh, here are the bounds of the world. Like you only want your agents to jump around in like the Central Park kind of environment. So when you're creating a property here, you just said, oh, here are the bounds. But instead of doing this, like we have a lot of utilities. For instance, you could be like, instead of setting bounds, I want to load the map of Central Park. And you could just do that. And like our documentation tells how to do that. And then your entire simulations will run in like a Central Park kind of environment. Okay. So you do that, you set up your environment and you're all set. Then the next thing you do is you describe a lot of behaviors, like what do the agents do? For instance, my simulation here wants to simulate how do the agents move around. So you say that, oh, for the citizen agents, this is the logic for them to move around. You're like, oh, so they have some kind of a step size, that the step size based on which they move each time. You say, oh, based on some random movement, I pick a step size that helps me figure out a direction for movement and what happens when they move, how does their position update. Describe that logic in a few lines of code, and which sort of just look like this, that, oh, for every person, I just figure out a random angle for their movement, I get a random direction, and based on the direction, I get a new position for them. So you just describe like a few of these lines, and then your model is complete. And once you've done completing the model, you can be like, so once you write a model, you write it once, you use forever. You can write a model for one kind of a problem, but you can use for a different kind of problem. For instance, we wrote this sample model that we just like implemented up. You take it, you just create an environment with this model and some population, like it's just some random population, which could maybe have 1,000 people, but you can also create a new population with 1 million people. And we've got like a tutorial to do that. How do you customize your own population? But you could, for instance, just you can load directly from the census, which population describes like all the citizens. So you just change the population, you set up your simulation and just write very simple Python code saying, oh, for these many runs of the simulation, each time I will run the simulation for these number of steps. So you just create an object of the simulation, you define how many times you want to run the simulation, you step. And like at the end of the simulation, you get like the positions for all people that you can visualize however you like. We have some support for visualizing models. For instance, like in a different model, we just ran the same simulation, but we wanted to, let's say, display the agents moving around in Central Park. They're just randomly jumping around, but we were looking at like, oh, they're playing some kind of a predator-prey game. And a bunch of these agents are jumping around in Central Park. So we have a bunch of display functions that allow you to run an arbitrary simulation you described, and then just say that, oh, I want to see what happens when they run around in Central Park. And we help you generate visualizations. Or we have tools to generate like even high resolution 3D visualizations if people sometimes want to use them. But in terms of code, it's simple Python code. We take care of all the acceleration, all the abstraction and everything in fast. And like compared to conventional agent-based models, it gives you a lot of benefits. For instance, to give you like a simple order of magnitude estimate, if you were to write like a similar model simulating like 1,000,000 agents, simulating like 8 million odd agents on like a very conventional agent-based modeling framework, even one that allows you to use high performance computing, you'll end up like your simulations will be really slow. You spend a lot of time calibrating them to historical data,
Right.
or you
Okay.
will spend a lot of time doing sensitivity analyses. But in our models, like if you design it using Agent Torch, if you use this Python API to write a model once, your simulations will be orders of magnitude fast. It implicitly comes with new algorithms to calibrate the model, which you cannot do in conventional APMs, but these calibration algorithms are like significantly faster. And then sensitivity analysis is also like orders of magnitude fast, that once you build a model in Agent Torch and you have calibrated it, you never have to run a simulation again to do sensitivity analysis. So it basically makes it as fast as like system dynamics models. And
Wow.
yes, you can compose it like within Agent Torch, you can compose it with system dynamics models, ordinary differential equations. You can compose it with like discrete event models. For example, when we do like some kind of a disease simulation, you want to figure out a continuous time process of like how is your immune system reacting, a discrete time process of how is people spreading infection in the city. But you also have a discrete event process of like people give stimulus checks 2 times in a year and you want to see how might people react to it.
Okay.
So all of these processes you can just plug and play together. Like our API allows to do that.
Wow. Okay. I'll sit back for a while. That's quite impressive.
Mike, what are you thinking?
Lots of things. No, it's very impressive. One thing I wanted to point out or draw the contrast, and Steve will appreciate this, between neoclassical economics, microeconomics, and let's say an agent-based modeling approach to economic problems. So in traditional neoclassical microeconomics, you have a representative agent. In other words, all agents are identical.
Yeah.
And it's just absolutely the opposite in agent-based modeling, and that's kind of the point, right? And similarly, economists have always, neoclassical economists have been accused of having physics envy. We want to be the natural science of the social sciences. And so, we're always looking for laws, the law of demand, the law of diminishing marginal utility and what have you. And as soon as you have laws, they have to be simple. They have to hold at any time, 1801, 1901, 2001, 2011, and they have to be, they have to hold across locations. Spatial aspects don't matter. It has to be the same in China, in Germany, in the United States, and whatever for laws to hold. So this is the physicist's way of kind of thinking about things. You start with your theory and then you derive a testable hypothesis. Then you look at the real world. Whereas system dynamics, agent-based modeling, sort of the heterodox or oppositional way of doing economics is to start with the real world and look at the characteristics of the people. They're not all the same. And if you want to build up to theory. So now you might raise the question, and well, are economists all stupid people who don't notice this or don't? Well, Steve says yes.
Yes.
They've had lobotomies. That gets in the way. They did a PhD in economics, which is the same thing as having a lobotomy. So they're pretty stupid. Yeah.
Yeah. Well, I don't know if it's stupidity or lack of intelligence, but I think this is my opinion. When economists started doing all this stuff, we didn't have computers. You built your economic models on a piece of paper with a pencil.
Yep.
And so by the very nature, you had to make these horrific assumptions about everybody's the same and what have you. And, they didn't even anticipate the computer, right? Well, okay, I get it. That's historically true. But then once the computer came around or whatever, how come you're clinging to the old ways? And I think it's a path-dependent process. Yeah. Why doesn't the United States fully go to the metric system with the rest of the world? It's obviously a better way to run the railroad, right? But so many people know their intuition is in the imperial system, not the metric system. all the machines and rule, we don't entirely blow the metric system off, but most, but we're so locked in to undo it. So economists are just trained by their older economists who are trained by older economists, and the textbooks, the journal editors, what they expect to see are just passed down. And you know how to butter your bread. You have to do the following to make a name in economics, because that's just the way it's done. So you have to be bold to break out of that mold. You have to say, I don't care if I get the acclaim of the majority of the economics profession, I'm going to do what's right. And when, 10 years in the balance, if you're a university professor or what have you, it's hard to do that. You have to be a rebel, like Professor Keynes.
So what made you move from light to people? What was why did you make that move from the Adobe to what you're doing now?
I mean, I think it's just a matter, just like things just happened like that. But I also feel like the problems that are of interest have changed. Like the initial click or like the phase transition was during like the pandemic when we had to build a lot of like disease models. That's why a lot of the reference problems for us became epidemiology, because the whole motivation to do it was like, oh, we would do like our stuff on the weekdays, but we were helping out like a bunch of these hospitals doing like disease simulations on the weekends to understand like how our like outbreaks playing out. And we realized a lot of the tools that exist in other fields can be used here. For instance, I'm of the personal opinion that like imaging and computer graphics is the best computational field, because all the tools that are built for imaging and computer graphics go to every other field. Like the entire AI revolution is built on top of GPUs, which were graphics processing units built for like a lot of the rendering and simulations we used to do. A lot of the modern algorithms that make like TensorFlow, PyTorch, and the big frameworks for machine learning work were built under the sort of design principles that made computer graphics work for a really long time. And I feel like more on terms of like the process structure, how you think of like, so light essentially is like a very system dynamics way of thinking about a problem if you consider it. Like how in system dynamics you think in terms of processes, people also think in terms of processes. There's like, oh, here is how you think in terms of reflection and refraction. And like then you look at like some kind of spatial characteristics. And then you look at an object engaging with this process, which being like a photon here, which is sort of how you think of system dynamics problems. So a lot of those problems on how they thought of simulations, I feel, are very broadly accessible to a lot of other fields. And people have done a lot of really interesting engineering work, which can accelerate all other fields if you make the jump. That's like one. But also like imaging and like a lot of like perception and computer vision has sort of in the last few years gone in a direction where like physical plausibility is no longer as important. Like in a lot of other like social systems where decision making is important, simulations and physics and system dynamics continue to be very critical. But in a lot of computer vision problems, which we care about around us today, like in some sense, like the physics is not as critical, or the simulation is not as important, because we care about photorealism of results a lot less. For instance, like a bunch of years ago, like the picture that you see from an iPhone, like you want your picture to look pretty, which means that it's like a data-driven problem. There is a lot of data about that problem. So we don't really need to simulate things as well. You can just build these large models that are very good at data-driven learning. And people mostly care about looking at pretty images. So it's possible to build models that can be trained on millions of images from Instagram, Google Images, YouTube, Twitter, everywhere, without having to simulate out the physics of light. And the outcome of the process is also, I want a pretty image. So when I click a picture on an iPhone, what I really want is I want a pretty image, not really a photorealistic image.
Okay.
In a sense, like you want it to look nice, it may not really be the actual image that gets captured. So a lot of like data-driven models can do a better job of capturing that process. And physics and like simulations seem to be more important when like photorealism is important. You want something to recreate an exact mechanics of a process, which is what we're seeing is starting to become more important in these other fields, especially in like health, economics, where like things are data sparse, there is a lot of heterogeneity in behavior. So like a combination of variables around like I like the simulation way of doing stuff. I feel that's what you can do in academia, where you don't have unlimited compute, unlimited data, unlimited resources. And like light and computer vision seems to be a field where like simulations are not driving the future at the moment, because data can like make up for that problem.
Okay. Mm.
Yeah.
Mm.
So Shot, welcome. I'm glad you found us, buddy. Listen, everybody, make sure you hit that subscribe button. That way, me and you, we can be together until one of us dies, essentially. So that's important. Hit the notification bell, so you actually see our videos. We started from scratch, right? Going on my channel, which compared to Steve's 80,000 subscriber channel and my 3,000 subscriber channel, there's been a bit of an impact to the weekly viewership. So if you're finding out that we've moved here, make sure you do those things. Subscribe, notification bell. If you're watching on Twitter right now, same thing. Well, you're probably following me at that point, but hit the notification bell. Come over here, come to my YouTube channel, subscribe, notification bell. If you're watching on my Patreon, you probably know about my X and my YouTube anyway, so there's not a lot to say. I think I want to actually download this Python package and try to create a small simulation for a stock index, or pardon me, an index of stocks, because I think that'd be really cool. That's kind of the next thing I kind of want to work on. And this is some interesting technology you got where I can scale so many agents, right? That would be very interesting. So you're probably going to see something on my Patreon pretty soon about me playing around with this. I will also, because I know a lot of people, Python's, in my opinion, the easiest code to learn. So maybe I'll do a little Python blog too, just so it's real easy to download. It's real easy to pip install your packages. So all the visualization tools and whatnot, real easy to use. The code's really easy to use. It's all indented code, right? So for me, it's a very beautiful structured code. And I think Ayush, would agree with me.
Yeah.
There. What do you think? Could we utilize your technology and build out a little stock market simulator? Do you think that's an applicable situation?
Yeah, for sure. Yeah, I'm definitely very curious to see how you use it in economics context. Definitely, like, yeah.
So
And yeah, and message me if you have any questions. It's completely open source. We have a Slack.
I'm
So
going
whenever you have
to.
any questions.
Yeah, no, I'm going to harass you about it. Of course, I'm very interested. So, a lot of people, if you want to kind of, maybe you've tried system dynamics because you've used Ravel, or you've heard Mike talk about what do you use, Mike? Stella. You use Stella, right? There is a package out there if you want to kind of experiment with agent-based modeling on a small scale, just to get used to it, and that's AnyLogic. So AnyLogic has discrete modeling, it has agent-based modeling, and system dynamic modeling. And that's where I've kind of just played around with agent-based modeling. I'm not an expert on it, but if you want to kind of get the small idea of what it is, and then maybe go download the Python package that Ayush is got set up, and then explore from there. That might be a good idea if anybody out there is interested. What is the link to your GitHub? Can you put it in the private chat, and then I'll put it in the main chat?
Yeah, for sure. I mean, there's the link to our GitHub, and this is the MIT project, which covers all the technical backgrounds, and you've got a lot of reading material, videos, and tutorials.
Is there a link to the GitHub on that page?
Yeah, there's a link to the GitHub, but
Okay.
I put a link to the GitHub also in the chat.
Okay. Oh, I see it there. Okay, let's put that one in and copy, put that one in. Also, if you guys are really interested in just getting into the GitHub but aren't familiar with Python, I'll tell you, YouTube and AI itself will teach you how to use Python. It is a great little coding language to learn. Steve, here it comes. Basically, what Ayesha is advocating here for is that you can use, define macro or from micro, essentially, if you have technology like this where you can scale enough agents. I'm not completely convinced. I think, like we've discussed, there's applications for system dynamics and there's applications for agent-based modeling. I would always say agent-based modeling, great for microeconomics. If I want to go model maybe a firm and 3,000 employees interacting, I probably go for agent-based modeling. But I still think I'm partial to system dynamic modeling when I'm observing a macro system. And as you said, most of our data from economics is aggregated data itself. So, but just knowing that we, and you've kind of discussed last week when I said we were going to have him on, that you've heard of these agent-based modeling techniques where you can have millions upon millions of agents. Do you think it kind of starts shifting the game where we can look a little more seriously at micro simulations and build it up into the macro? Does that kind of change the landscape again, or do we still have all the same boundaries as Anderson pointed out in 1973 in his paper that none of the other sciences are building up macro from micro? Why would economics? Kind of what's your summary on all this, and including the fact that Aish has some pretty good technology going on? Silence.
Well, that's to me the issue, because one reason that Mike and I and Ty all do the top-down modeling is that there's an obsession in economics with bottom-up modeling based on 19th century concepts about how one does modeling. And to do it, they've shoehorned everything into so-called rational agents. If we're all individuals, we're all exactly the same, the representative agent thing. They're getting to what they call Hanks now. It's the stand for heterogeneous agent new Keynesian models. So they're starting to do something in that direction, but they're still imposing so many elements on it. And as Ty was saying, if you look at the DSGE models, they basically impose the final solution. So what was first called the bliss point by Ramsey when he built his model of optimal savings model back in 1928, the equilibrium was unstable. And so they have all these numerical techniques to make sure the system converges. They rule out behaviors which are going to give you eigenvectors that lead to instability, et cetera, et cetera. So all that stuff makes us very critical. So we prefer to do the top-down modeling. But are you going to attempt a macroeconomic model with these interacting agents where you've actually tried to describe the actual nature of each agent, statistically speaking, across the whole of America? Is that one of your ambitions, to produce a macroeconomic model based on micro behavior?
Silence.
Just asking, is that what are you directing? Are you going to attempt one of these large population model to actually simulate the American economy?
So again, I agree with part of your question. So yes. So not from an economic sense. So the way we are starting is I wanted to do a bunch of the labor market stuff, because my hypothesis is problems where not just processes, which a lot of the macroscopic models capture, but also heterogeneity in behavior matter or heterogeneity in behavior at an individual level or at a spatial level. When those start to matter, I feel the benefit of agent-based modeling will become more explicit. So so what we're starting to do is can we simulate out the labor market? Because there is a lot of spatial behavioral heterogeneities that will start to play a very critical role, especially as AI starts to become a critical part of the workforce in many scenarios. So in those cases, for instance, what does it mean to be a median earning welder or a mechanical engineering Tennessee versus in Seattle will have very different consequences and implications of the same kind of AI automation. So in these kinds of scenarios, yes. So our current goal is, can we do the labor market bottom up with an agent-based model?
But to do the labor market, you've got to have the macroeconomic factors that are driving the labor market. So are you looking transitions from human-based to AI? Or are you looking at the booms and slumps that we're seeing in macro data right now with unemployment rising in America, Because we're into feedbacks and what causes booms and slumps in a capitalist economy. Is that something you hope to model, or are you staying at the ambition of modeling behavior within the labour market subject to a range of inputs, like, for example, the development of AI?
Yeah, I mean, so we've started more precisely. So like this project is specifically more focused on the transformations linked to AI. But in the past, we've done actually some like, I would say like labor adjacent work. For instance, we had a paper earlier this year, which basically we started during the pandemic. There were things like we started by modeling disease outbreaks, which have a similar structure where like I mostly care about like most of the data you get is about infection at an aggregate level. But what we were trying to show is that if I do disease simulations in a bottom-up microscopic level, can my models inherently predict outbreaks better than a lot of the macroscopic aggregate system dynamics models? We showed that, but what we tried to see is that how do interventions shape behavior? For instance, we tried to see how do things like a stimulus check will change disease outbreaks by altering, let's say, labor force participation behavior. So what we showed in our bottom-up simulation was that we basically built like this digital simulation for New York City. Through our disease and like labor force participation simulations, we were able to predict disease outbreaks really well, and also actually recreate the BLS's like labor force participation survey entirely in simulation. So for us, like that was a metric to say that can we predict it in simulation for like a few $1,000s. And we wrote a paper early this year where like, yes, we are able to like at least predict a lot of these behavioral artifacts. So instead of trying to go entirely to the big problem, with like these tiny pieces, we're starting to show that in the context of like, if you go like the way large population models build stuff, where you can capture extremely rich behavior models, where like you can have like 8 million agents, but all of them be like LLM driven. Or you can have like, you can calibrate your environments to actually macroscopic data. Like even in the context of disease, we have macroscopic data, the kind of macroeconomic data you're describing. In those cases, like you can start to get interesting results. So yeah, we're slowly building up to it.
So we've got, can we think of agent-based modeling helping improve a macro system dynamic model like ABM for banks, so as to understand certain dynamics in the financial sector that can that inform specific feedback loops? That's what I was kind of talking about earlier, that it would be lovely. And on the geeky side of me, I would love to build a model where I could drill down to the micro and see the dynamics within, let's say, a financial institution or a group of financial institutions. And then, of course, the question comes in my mind, do those small scale dynamics really change the macro dynamics? And something I would have to explore. One thing I was thinking about while we were discussing this, Mike, I know agent-based modeling wasn't around in Jay Forster's time, but did he ever talk about the difference between macro systems and small scale systems? So did he ever talk about either he didn't like building up from micro, or he saw maybe there was applications for it? Did he ever talk about that stuff, or was he just focused on top-down systems?
No, he talked about it in Industrial Dynamics in 1961 in the magnum opus of system dynamics. And Jay had no problem with looking at sort of the agent-based level of things. He just felt it was easier to start at an aggregate level and then go from there. But he had no issue with what we would today call agent-based modeling. I think just a couple of comments based on the conversation so far. I think one of the problems that many economists have had over the years, when they kind of think that there's no need for macro because the macro economy is just the sum of the micro economy, just add up the individual behaviors, is that, yes, that's true if the system is linear, right? But as soon as there's nonlinear interactions, that is not true. And that's why we have macro. Keynes told us, it's a fallacy of composition. If you think what's true for an individual or an individual labor market is true for the aggregate labor market, that's wrong, right? If you save more, good for you. If I save more, good for me. If everybody saves more, ceteris paribus, you throw the economy into a recession, right? So he showed us that. That's why we have macroeconomics. So there's sort of a mathy explanation, the linear, nonlinear, superposition property thing, and then just the logic idea. So we have to treat the aggregate behavior, even if there's micro foundations accordingly. It's a nonlinear system. Now, one of the areas where, and I love ABM, I think it's really great, but one of the areas I think it's a little bit deficient, and system dynamics is deficient as well, it has its cons as well as its pros, is when people ask you, that's really interesting, I didn't expect that. And that's big in agent-based modeling because the behavior is emergent. But even in a system dynamics model that you've built yourself, and you'll say, let me show you 10 interesting simulations. And you show them, and then somebody yells out, try this. And you try it, and something really different or weird and unanticipated happens. What do they ask? Whether it's an ABM emergent behavior or that scenario, why did that happen? And a lot of times I've built the model and I'm like, hamina, I got to get back to you. I don't know. I can't tell you why whatever just happened. It's interesting. It's cool. But I got to do a deeper dive. So that's system dynamics. It's tough as well, but we have tools that we're developing like loops that matter that provide a feedback explanation for why something has happened. And I think ABM, it's tougher to pull that one off. The other area where maybe system dynamics has a little bit of an advantage is this. In terms of policy, which is, I've said it a million times, redesigning the airplane. We're not going to throw the airplane away, but the airplane is not doing exactly what we want it to do. We want it to fly higher, faster, more fuel efficiently, carry more cargo, more quietly, less emissions, whatever, right? So we want to change things around. Where do you redesign the airplane? Do you change the landing gear, the flaps, and we find with nonlinear feedback systems, particularly those that have a lot of negative loops in them, goal-seeking behavior, you can pound on these things here, there, all over the place, and you don't change the behavior. It's still basically the same. You can shove it around a little bit, or you'll get what you want in the near term, but it goes right back to where it was in the longer term. This is why, if you would, I will paraphrase B.F. Skinner, one of my favorite, I like the way I say it better than B.F. Skinner, but his idea was that if you magically transported the ancient Greeks to the present day, they would understand absolutely nothing about our technology, but they'd understand absolutely everything about our socioeconomic environmental problems because they have not been solved in thousands and thousands of years, right? These are your grand challenges, your wicked problems. These are entrenched. And like in our modeling, these feedback systems, you beat on them here, there, and everywhere, and it doesn't change. So you need to look for leverage points in the system, right? This is where shifting feedback loop dominance, tipping points. And we have tools or are developing tools in system dynamics to find those, because that's where you intervene, where you can apply some resources, time, money, whatever, and change the way the airplane flies, presumably in the direction you want. And I think ABM, it's tougher to even identify. There's lots of feedback loops in ABM models, but where are they? Identifying them and then using that. Now, so again, it's not as one isn't better than the other. It's just there are challenges and pros and cons of each tool.
Thanks. That's a very interesting thing. I'll push back a little bit to that.
Good.
Because ABMs historically have had that problem, but you can actually solve for it computationally. For instance, a lot of the continuous time system dynamics models are easy to analyze, or they have very structured way to do sensitivity analyses, is because they have this property that they are made through a combination of differential equations.
Yeah.
And when you have a combination of these differential equations, you basically have the gradient. You can always say something like dy by dx exists. And that's a very good measure of sensitivity. And you can use it to and when you use this gradient on a Hessian or some kind of a Jacobian or some other some statistical measure, you can use it to study stability properties or all the other kind of sensitivity analyses, equilibriums that you study come from this property. So what it really means is you need systems that need to have the ability to be differentiable, or where you can compute these kinds of partial derivatives from between any two variables that matter in the simulation. So we basically brought the same ideas from continuous time systems to actually discrete time agent-based models. So if you build like large population models, they're also inherently differentiable.
Okay.
So in a large population model, despite them being stochastic, discrete time, discontinuous in structure, if you write it in like a framework, they're inherently always differentiable. So any two variables between the input and the output, there always exists a partial derivative. And we've done like a lot of work inventing new gradient estimators, which can sort of help you sort of to take gradients for like discrete things like Bernoulli's or categoricals or like things that are discontinuous. So, but if the whole point is like, now that we have solved those problems, everything that allows you to analyze the dynamics of a system, which largely comes from like the gradient properties, you can actually now do in a large population model also, which is why you can do sensitivity analysis fast. But it gives you an extra benefit that you can do sensitivity analysis not just with respect to the dynamics, but you can also do it with respect to behavior. So all the feedback loops you're talking about, like they become more interesting in an agent-based model, because I can see like feedback loops between like behavior and some dynamics of the environment. And this is actually very standard in epidemiology. Like you have things like why do always waves of a disease happen, even if a virus doesn't change? It's because like when infections go up, people get scared, they sit at home, they move around less. So infections come down. But when infections come down, people become more conservative, became more like relaxed, and they start to go out and infections go up again. So these kinds of feedback loops always play out in systems. And when an infection goes on really long, you'll see like the waves become bigger because things like pandemic fatigue kick in, where people are like too tired to sit at home, which further shapes behavior. Or you might see that if it goes on for too long, suddenly infected people give a chance for the virus to evolve. And then there is a new infection and a bigger wave comes in. So these kinds of feedback loops between behavior and an intervention and an environment, you can capture more explicitly now in the context of an agent-based model, when you can basically at the same time measure, like, if you have the ability to do differentiability. So
look at you, Steve.
Talking about pandemic fatigue. I just thought I'd throw that little one in there. So I avoid the fatigue because I've got this little cooler here. Every time I go through an airport, I'm told I'm the only person they've ever seen using the bloody thing. And the reason I use it is because I don't suffer from fatigue because I'm breathing cool air. So anyway, my technological solution. I am the only agent on the planet that uses this damn thing.
See, an agent-based model can test for the effect of that intervention on the people around you at the airport, because we can see.
Go ahead, Mike. Actually, go ahead. I'll go after.
I was just going to respond a little bit. I have no doubt that every day people are making around the world advancements in ABM technology, where what was true 5 years ago or whatever is not true any longer. So and hallelujah that we're making progress in the simulation sciences in these areas. The point I would make though is when you do consulting with public or private sector, I've done a lot of court cases recently, expert witness court cases. I've dealt with lawyers.
Okay.
You're never politicians, CEOs. You're almost never dealing with, let's say, an engineer or a mathematician by training. Yeah. You're dealing with people coming from accounting, finance, or what. And as soon as you say Jacobian or derivative, they wet themselves. They want it at the kindergarten Crayola crayon level. In plain English, tell me what the hell's happening here. Why is this happening, right? And so the challenge then is to take the tools that are being developed, eigenvalue, elasticity, whatever they may be, and say, all right, to the average citizen, what this means is as follows, right? And so, otherwise it's just academic gymnastics and we write papers for one another and we pat ourselves on the back on our brilliance, but the world goes on crappy.
Makes sense. Yeah,
that's because crappy people are in control, which is part of that story there. Yeah, and this is for the person wanting the black one over there. Beat you to it. Sorry.
Oh, you have different colors. You can match when you're wearing a tuxedo, you can wear the black one, right?
That's right. Actually, I have the bow tie. I've got that on my phone these days. I might go and give that a try.
Oh, gee. Yeah. I add on for one. the reason why I've kind of steered this conversation, it wasn't about system dynamics versus agent-based modeling. It was really, let's talk about those two simulation tools as opposed to conventional economic simulation tools.
Yeah.
Right. That's really what I'm getting at too. And what I feel about it is they're complementary systems, right?
100%.
Depending on what you're going to use them for. I was going to say something else. Oh yeah. So you were describing a phenomenon where people lock down and then the virus dies out and they come back out and they stop their lockdown procedures. And you're describing a wave phenomenon. And Steve and I met almost 4 years ago, and I had built a system dynamic model. And the thesis of that model was those waves were caused by lockdown fatigue and policies going off and on, as opposed to new variants of the virus. Did you discover that yourself with one of your agent-based models? I'm just kind of curious.
I mean, I wouldn't take credit for this. This is like a very well-studied problem in like epidemiology, and people are all like, so it's like well established. Like with agent-based models, you can see this hypothesis, but we're not the first to observe it. Like people have been observing it for like over a decade, that infections seem to follow this wave pattern because of like feedback loops between behavior and the environment in some sense. Yeah.
So just to confirm it here, Aish has confirmed that the waves that we see in flus, pandemics are generally caused by off and on policies and people getting tired of those policies and not following them as the disease spreads over time.
Or yo-yo dieting. You know, you go on a strict diet, you lose weight, and then you look and say, I'm good, and you start eating chocolate bars again. You know.
Exactly.
How many? Just to give you a bit of a description of the size of your team, Ish. How many people are working with you? What backgrounds do they have? Because it's a fascinating. I mean, what you're doing. We obviously we're all top-down people in our nature, but we love what you're doing to make bottom-up be non-homogeneous, and then get those interactions. So tell us about the team. Are you doing a PhD? Have you done one? All this sort of academic background.
Oh, I'm doing a PhD. I'm in the third year of my PhD. I'm almost done.
Okay. Yeah.
And yeah, I mean, this is like Agent Torch, and like this is like my PhD project. So it's largely me, but like on specific projects, I've collaborated with a lot of people.
Okay.
Like or different part, like tiny pieces of the problem. We've worked with like people in like a lot of public health and epidemiology. People motivated a lot of application work in the beginning. We've done like more of the quantitative work. We've collaborated with like people in like just simulations and like multi-agent systems and a lot of like the conventional computer science domains. We had like some collaborators in like some more like economics domains, especially especially out of the UK and Europe. There's like a lot of really good like complexity economics kind of work that's happening there. So most of the technical work is like largely, and like then there's like a lot of open source people who contribute to the framework. So we've got like around 8 or 10 people who actively contribute to the framework. There are a lot of people on our Slacks who are discussing. Our Slack is like people in around 20 time zones at the moment who are always like contributing ideas or discussions and like collaborating on papers. So it's a very fluid collaboration, mostly out of like outside the university, not as much inside.
Okay.
But with like people from like very diverse experiences.
Okay.
So,
okay.
Yeah.
So your motivation, would you say you were working at Adobe and you resigned from Adobe to come and do the PhD?
I mean, I came to do computer vision and graphics and those kinds of problems.
Yeah.
Like the pivot happened after. But yeah, I left my job to come to do my PhD, hoping I would continue doing the kind of stuff I was doing before. But then like the pandemic happened, and that was sort of like the tipping point for me to like jump into like an entirely different world.
Okay.
But yeah.
So in layman's terms, this guy here is extremely smart. I shouldn't bring smart people on my live stream because it just it takes away from me. Like I just try to talk smart, and this guy, he's a freaking genius here. Yeah.
So what's an interesting thing in economics is the economics profession is that to the extent that nonlinear dynamic modeling has been accepted, it's ABM instead of system dynamics.
Yeah, that's right.
And or possibly, if you want to say difference equation modeling, although that's often just linear modeling. But and the system dynamics people have always scratched their heads because system dynamics is an older discipline, not by many decades, but it's a bit older. So why is ABM caught on among economists much more readily than system dynamics? And it's been speculated it was Jay Forrester's personality and his clashes with economists, or the world models.
Economists are too stupid to understand system dynamics. That's why I'm with Jay Forrester, even though he turned my bloody paper down.
I think it's actually there's an appeal for micro foundations, right?
Yeah,
and
that's
so,
right. Yeah.
Now, I think trained conventional economists don't understand the micro aspects of agent-based modeling, but just hearing that it's a bottoms-up approach, that might be very attractive to a conventionally trained economist, and maybe that's why we're seeing more fringe cases of agent-based modeling in economics as opposed to system dynamics modeling. Something I've thought about in the past too.
I think that's the major factor because, I mean, they're just, they used to talking about the rational agent does the following thing. And so it's minor, the micro foundation bias, which is a fallacy in economics, is why that when you give them a choice between system dynamics and multi-agent, they'll go multi-agent in a heartbeat. But you're coming in, I mean, your smarts on multi-agent far exceed what most neoclassical economists are capable of. Some of them know what a Hessian is. But I'm not going to, they work in discrete time modeling. Their Hanks are all discrete time, T and T minus one. They're not. Actually, one other question I must ask you: are your agents operating in asynchronous time?
Our agents, yes.
Good. Okay. That's an obvious thing because if you work in complex systems, you know that everything happens asynchronously. But the habit that neoclassicals have got into, and this affects stock flow consistent modeling as well, everything happens in T and T minus one. So we all invest at the same time and we all consume at the same time. And we base our consumption on last year's income, which is nonsense. Okay? So that's one of the traps of the multi-agent. But with the background you've got, you're aware of all that. So, you didn't even need, obviously you work with asynchronous behavior. Because that's what agents are like that. So, yeah.
So
interesting.
Sorry, I don't want to interrupt.
So
earlier today, Steve asked about, how do you sort of write the rules for the agents to follow? If it's a physical system or even a biological system, kind of nature defines what the rules are. But for humans, they use rules of thumb and what have you. And this is where behavioral economics, experimental economics might have a nice fit with agent-based modeling. And in fact, in our research group, I've had some of our doctoral students working on this issue of taking what's known by or been discovered by behavioral economists, and how do you put that into a system dynamics model in a manner that would be accepted by behavioral economists. So the first thing I have the students do is replicate some papers from the economics literature exactly. And it's like, okay, you all might not use system dynamics, but our graphs are identical to your graphs. So we're nailing what you guys are doing. And then it turns out that the behavioral economists and experimental economists tend to almost always use discrete time.
Yeah.
Although they say in a variety of places, we're not opposed to continuous time. And there might even be times where that makes sense. But the few who we've observed who've tried to do continuous, they're economists, behavioral economists trying to do continuous time modeling, they do it horribly typically.
Yeah.
They're just not trained to do that. So for a variety of reasons, they probably stick with the discrete modeling. So I've had the doctoral students bring their discrete stuff into system dynamics models. And it takes a little bit of fiddling to do that, but you can do it. And by the way, Forrester never objected to doing that either. I mean, we have pipeline delays in system dynamics. We have Boolean logic. And so you can put stuff in there that's discrete in nature when it makes sense. So there's nothing that it doesn't imperil the paradigm or anything. But then you get into, all right, should you take the otherwise continuous time system dynamics model, and where it makes sense, put in a discretely modeled insight from behavioral economics, like present bias or prospect theory or anchoring and adjustment, or whatever these folks have found out that people really do. And because you can do it, you can put a discrete thing inside of the otherwise continuous SD model. Or I've had the students translate that thing into continuous time as if it's hopefully identically, or if not identically, as close as you can possibly get. And we've gotten some good results there. So then do you say, no, take the continuous time version and put it in the continuous time model? Or then now we start freaking out the behavioral economists, they don't believe it anymore, or do you leave it? So this is an issue. But my point is, the larger picture point is, working with behavioral economists, for that matter, psychologists, decision scientists, and whatever, to say, what do people really do when they make their economics decisions, and how do we put them into our ABMs or our system dynamics models? I think that's very important.
For sure. And I mean, I haven't done as much work on this specifically, but there are a lot of like really interesting people in like the agent-based modeling community who are like writing really interesting papers on like bounded rationality for agents and agent-based models, coming from both like the sociology and the computer science point of view. There are also like a lot of the AI and the multi-agent people who are getting into this. So like there's a lot of work, especially coming out of like Oxford. There's like people out of like the Institute for New Economic Thinking in Oxford who are doing like a lot of really interesting work from this point of view. But fully agreed, yeah, very interesting problems.
Yeah, and it's not just that, hey, we want our models to be more realistic. We do, but people like Dick Thaler have said there's policy space there. So how do you get people to save more for their retirement? He finds that they because of present bias, I think it is, they won't save more from their current paycheck, but they will save more from their raise, right? And that's exploiting, policy-wise, exploiting an insight from psychology, right? So I think it not only makes our models more realistic, but it opens up policy space for us.
So we've got, just maybe Aish or Mike or Steve, you can answer. I don't quite understand Ralph's question. Isn't probability a significant part of going from discrete to continuous? I'm not too sure what you mean. Maybe add a little more detail to that. I'm just curious.
Obviously, you're working with discrete time modeling, run the discrete time, but you're working with agent-based, then you're going to have, you don't actually have data in every last agent. So like you were talking about taking in census data. So what you'd be taking is census data about, how many men and women there are in different districts, or what the income, what are the job proportions that exist in a particular zip code, and then but you have a probability distribution to match that, because you don't have data on each individual agent. You have a probability the agent will be doing a particular job. Does that turn up in your code as well?
Yes.
How do you see that? This is trying to make a bit of detail for Ralph's question. How do you go from the census data to how you specify your agents? Is it via probability distribution?
Yes, I mean, this problem shows up a lot because like usually you have census data maybe at a zip code resolution.
Yeah.
But you have very different aspects. You've got like demographics and employment and economic and like workforce and a lot of this information, but at a zip code level. So inside a zip code, we basically generate a lot of these synthetic populations, which such that like we generate like, if a zip code has like 1,000 people, we'll generate 1,000 people inside that zip code in such a way that in aggregate, the 1,000 synthetic people we generate, their characteristics in aggregate match the characteristics of the real population that we got.
Right.
And there's a lot of interesting work that's happened in agent-based modeling in the last few years. I mean, I'll call out like some of the works from like Oxford has like an interesting group doing like a lot of like multi-agent systems, which have written interesting papers on like how you can generate synthetic populations by like fitting to real world data. So people basically use the simulation in itself, like they've extended some of our differentiable simulations and stuff, so that you can use the simulation itself to generate the synthetic populations, which are well calibrated to the zip code level data you get. So okay. Yeah, so like we have to like spend a lot of time sampling populations. So that's why it's always like a equivalent population. It would never be like an exact match of the real world, but focusing more on like the scale and the heterogeneity of attributes and the distribution of traits is consistent.
Okay.
So one of the problems we found over the years in getting economists to accept continuous time modeling is this obsession, and it comes from training in econometrics, of fitting models to data. And of course, at the macro level, data are released according to the economic calendar, right? Monthly, quarterly. So there's a data release, nothing, data release, nothing, data release, and so forth, right? So it almost screams discrete difference equation modeling. So, but you say, well, but things happen in between the the two data releases. So hence continuous time modeling might make sense. But here's the problem more specifically. I'll give you an example. I was once sent a data set, a very simple data set, an Excel spreadsheet from somebody who read one of my papers and said, I tried to do system dynamics like you argued, and it sucks because I can't reproduce my data set. Here's my model. Here's my data set. Now, it was very simple. The data had 3 columns in an Excel spreadsheet: production, inventory, and sales for a company. And I think it was a long time ago. I think it was weekly. It might have been monthly, but I think it was weekly. Okay. Mm-hmm. And so what this person did, it made a very simple system dynamics model: an inflow of production, a stock of inventory, and an outflow of sales, right? Mm-hmm. Makes complete sense. And this person used a table function to put in the exact data of production from this company into the inflow, had initialized the stock at the first inventory data point, and then this person had the sales data and ran the simulation. And the inventory and sales data didn't match exactly. Therefore, system dynamics sucks. It should fit the data perfectly. I mean, I gave it the exact data, right? Well, what this person didn't realize is that, let's say, take weekly sales data. Let's just pick that. Is Monday sales plus Tuesday sales plus Wednesday sales plus Thursday plus Friday sales. As soon as I say the word plus, we have a stock. We're accumulating. There's an integral in there.
Yeah.
And you say, well, just Monday's data. Well, that's 8 o'clock sales plus 9 o'clock sales plus 10 o'clock sales. Mm-hmm. So there's the data that are released by the Fed or wherever are not the instantaneous rates or flows. There's a stock in there calculating the number, right? Because the flows in a system dynamics model approximate an instantaneous change in something at a moment in time. Now, it's not exact because a digital computer cannot take infinitesimally small steps in time. They can make very, very small steps, but that's what it's approximating. So it should not match exactly. Economists cannot wrap their head around that one.
Yeah. Are you dealing with economists a lot in your work, or are you fortunately insulated from them?
Me?
No, I do. Oh,
no,
sorry,
not you.
Sorry,
you.
My bad. I didn't.
No, not as much. I mean, we've had very limited. We work with a lot of mostly computer scientists on the application side. Some people who work in complexity economics because they're more interested in the methods, but not as much directly working with economics. But I'm very curious to know how do you what's the blocker because the complexity economics people seem to be really aware of the problem, but why do you think it's not going mainstream? What's the argument against it?
This is the mainstream. The mainstream is completely resistant to anything that doesn't get to equilibrium. It's become a religion for them, a fetish, and they can't break out of it. But I've actually got. I'm teaching at the University of Amsterdam now with a couple of colleagues who are both multi-agent modelers. One is building a multi-agent model of Canada, and the other, bloody Canada. I can't get away from Canada. And the other is building a model of the Netherlands.
Canadians.
And they're bloody Canadians. But so Kars Holmes is one. He's working at he's working with the Central Bank of Canada right now, building a multi-agent model of the Canadian economy. And Stephen Hoekstra is working with the Netherlands Central Bank, building a multi-agent model here. So there is some progress in economics. There are people who are open to these ideas. So I've put the links to their names in the chat. They do take a look and do get in touch because they're economists you can actually have a sensible conversation with.
Makes sense. Bank of England also seems to be doing a lot of work. I've seen a lot of
Yeah.
ABMs for central bank working papers usually come out of that place.
Yeah.
So
They hired a number of physicists a while ago, and they've still got them in the research department. So yeah, there are pockets. There are some decent pockets there. So yeah, you tell us a bit about you said large population models, and it sounds like it's something like the matrix transformations involved in large language models. Is that correct? To get that processing speed improvement you
Yes.
were talking about? Okay, so tell us a
So
bit about that.
yeah, so we do a lot of like the matrix operations running in parallel, leveraging the acceleration abilities of GPUs to make sure the simulations happen fast. So
Yeah.
that's like part of it, but we also invent new algorithms where you can basically calibrate these models better, which provides a lot of benefit. For instance, like when you're trying to fit these models to data, a lot of cost goes into like people end up building these things called surrogates, where they basically take this model, run a lot of simulations, collect a lot of input and output data, and then like take this input data and build some kind of a surrogate model for calibration. They'll have some kind of like a simplified model, like a mixture model, a Gaussian mixture model, or a linear regression, or some kind of a neural network which runs offline on a lot of this trained data. So we built like new algorithms that allow you to directly calibrate your simulation without having to build a surrogate. So it's super fast, doesn't require as many simulation rollouts to happen. We use a lot of like the vector programming and like a lot of the ideas that have made machine learning go fast on GPUs to make these simulations go fast on GPUs. So everything runs through like large matrix operations. We use a lot of sparse tensor operations. And to give you an example, for instance, think of New York City. That is 8 million people. So if you have 1 million of 1 matrix of 8 million by 8 million, that is 64 trillion operations actually. That's too much for any computer to do fast enough. So, but if you leverage the structure of the interactions in the real world, you'll realize, for instance, that the world is a very small world. Like there might be 1 million people in a city, but on any given day, people will meet like 5, 6, 7 different people. So graphs have this like small world structure. So when every person is only meeting 5, 6, 7 different people, what I really need to process is not 64 trillion interactions, because most of it is zero. People don't cross paths with most of the people, but maybe like 60 million, like 8 million divided by maybe 6 multiplied by maybe 6, 7, something like that. So that is significantly less than 64 trillion. But to do that, we leverage a lot of like these things called sparse tensors, which allow me to store the full matrix without having to store every entry. So I only store the entries that matter, and we do a lot of this algebra like that.
In my Ravel software, that's one thing we had to do, because when we first designed it, we had a dense matrix outside. So if you have, a 10 by 10 by 10, you had 10,000 interactions coming out of that, and you might only have 35 data points in the whole damn thing. So to make it fit, we had to bring in tensor mathematics and sparse data matrices and so on. So we've done the same thing. It gives us the same sort of speed improvement, but of course, what you're handling, 230 million agents or 330 million agents, you desperately need that, because otherwise the number of combinations is simply overwhelming.
So
yeah,
let me hop in and ask a little bit of a provocative question. So when we do modeling, presumably we want to simplify the world. We don't understand the world. So presumably we don't want to make a digital twin, an exact replica of the system we don't understand, because then we would have a machine version of the thing we don't understand. So we want to simplify it, find the important stuff and leave the unimportant stuff out with respect to whatever our problem is. So let's say, we want to model whatever the United States economy, and there's 330 million people or 100 million households, whatever you want to say, right? And you say, well, we got to use all these matrix algebra tricks and techniques and cleverness to be able to solve the thing in a reasonable fashion, in a reasonable amount of time. Why not just say, well, 49% are women, 51% are, I guess probably the other way, 51% are women, 49% are men. Of the 49% that are men, there's 15% are rich, 47% or whatever, and whatever other categories you want to do, and say, let's just take 10,000 agents with those proportions and run it, rather than trying to do all this, millions and millions of agents and hence calculations.
So it depends. So that's a very interesting question. That depends on the kind of problem you're solving. So we actually have done work on this. So we have had a paper this time trying to say that if you have limited compute, what should you do? Should you have a few extremely rich and detailed agents where like instead of having a full city, you capture maybe like 1,000 people, but you describe everything you can about them in scenario 1. Or in scenario 2, you take everybody in the population like full scale, but you have very little information per person. And turns out like if you ask like which is better, that depends on the kinds of question you care about. For instance, when we were trying to predict disease outbreaks in a city, we realized that having a lot of really simplified agents results in significantly better quality of predictions than models which have few agents with a lot of detail. Because in like large systems, like agent-based models seem to be more useful when interactions between agents matter. So for instance, like the way you're describing a population, that can be extremely useful to answer questions where most of the behavior is driven by the intrinsic capabilities of a person. And in that case, looking at just probability distributions and demographic structures can be enough. But when you have questions where like interactions dominate, like people may not do a lot of things on their own, but infection spreads through interactions. Or similar things that happen on like supply chain networks when you're moving goods over like a scenario, or like placing inventory inside a fulfillment center, or you're trying to look at like marketing campaigns for the same product in different zip codes across the country. When interactions and social networks and influence matters, in those problems, it's generally like what we've seen is like it's better to over-index on capturing the full population, even if you capture little information about people, rather than trying to build simplified approximations. So it just depends on the question.
So, okay. So I want to push this idea of quick, maybe not simple, but the ability to build a model fairly quickly, or everything's relative, but fairly quickly a little further. I've done some work out at Sandia National Labs, and I have placed students there. And so I'm a little familiar with those folks. And they're one of the national labs that the U.S. government relies upon for to answer various questions. And they basically say, you know, it's a pretty nice low pressure place to work until something bad happens. Well, let's pick something from the news, an earthquake leading to a tsunami, right? Mm-hmm. But it's a shock to the system. By definition, you didn't know it was coming. And they said, when that happens, put clean underwear in your desk drawer, because you're in the lab until whatever department in the government, they want an answer. And they want you to run simulations or whatever and tell us what to do. We need it yesterday, not tomorrow. Right. So the ability so they were working on techniques to build, in their case, system dynamics models more quickly using generic structures and whatever, because the secretary of XYZ wants to know now. Get on it. Right.
Oh, so okay. So you want to know more about the speed of development. That's so actually like, if you use our framework, so we've optimized it over the last 4 years just to really go down. Like now we can actually build like a country scale simulation in like 3 hours. So if I sit in the morning, I'm done by the afternoon. But like we've built a lot of underlying structures that allow me to do that. When we started like during the pandemic, when I built the first model using all these design principles, it took me 3 months to write the first one. But we've like exponentially come down in time that now with the API, we're able to get a model in like, I mean, I'm able to write it in 2 hours. And like the documentation is easy enough that we have new developers who come into the platform and have like their first model ready in like a day or a couple of days for people who don't have as much experience. So it's pretty fast. And like this auto scaling happens without you having to do anything. So like all the engineering has been like weaved in part of like the infrastructure.
You basically build a huge library for people to use to build any form of multi-agent simulation.
Yeah, we built like a lot of these like general purpose operators that you can just put together. Like they're simple Python code. And that's why we basically use the same API as PyTorch, because like PyTorch, a lot of people use in machine learning. It's the standard. So we basically took the architecture of writing a PyTorch model and just swapped out the things underneath so that you don't worry about what's happening underneath. As long as you know how to write Python code, you'll be able to write this model. And like in terms of development time, it's pretty fast now. We're able to do it in a couple of hours.
Okay. So if I wanted to build a macro model, like my model of Minsky's financial instability hypothesis, how would I do that in your code?
I mean, you just go and, we have a bunch of tutorials and documentations, but like you just install the repository. We have this core module called the substep, a substep is like is a process in the system. So the way we write the simulation is you describe all the processes using our template. So it's like process 1, process 2, process 3, and then you get to compose them in whatever sequence you want. And once you've written it, it's basically like a Lego block. So for instance, if you model system 1, which has like process 1, 2, and 3, but then you want to build a separate model, which is process 1, 2, and 4, you don't need to rewrite the entire model again. If you break it down into the same process structure, you can just copy over 1 and 2 and just write a new service 4. And like everything that you describe in a process automatically gets connected to the state. So our simulation takes care that, if process 1 is about age and gender, process 2 is about income, and process 3 is about something to do with like age plus income. And then you get a process 4 which is about like your zip code. Then like the system automatically takes care of like how to handle the state and description of each person if you just describe the process. So you just clone it, you write the 3 processes, we call them sub-steps since they're part of each simulation step. At each simulation step, all the sub-steps get called in sequence. So you write all the sub-steps, these processes, then you describe a population. If you just want to test it, there are already sample populations to work with. So you just import a population, you import a model with your sub-steps, you call one line of code and your simulation is running. And if you want to change a sub-step, or if you want to change your model, you just change the process you cared about. And it's quick iteration loops. So when, for instance, like the problem you're describing that, suddenly a new kind of a hurricane happened. So those are problems we care a lot about. Because in disease, it's like we have this disease model, but suddenly a new kind of virus has come out, which behaves slightly different. Or we've put out a new kind of an intervention in the population. That I just launched some kind of like a lockdown policy, or just launched a new kind of a vaccine strategy that works in a specific way. So in those kinds of models, you don't have to touch the rest of it. You know how a population reacts. You know how disease spreads. You know how infection transmits. You just have to add this one Lego block, the specific process, and your models are fully backward compatible. So like it's easy to like progressively build on top of them.
So what do you think is the future of this sort of modeling, whether it's ABM or system dynamics or whatever, and artificial intelligence? Is AI going to replace these tools or be integrated with these tools more directly, or what do you think?
I mean, I feel like it's very integrated very strongly, which is also why I feel like the era for bottom-up modeling is going to come even more strongly, is because a lot of the people who we see get interested in, for example, modeling these days, or like they like agent-based modeling because like with LLMs, like there's this huge focus on like LLM as an individual agent or an entity. So a lot of people who are getting into this field are coming from a very bottom-up way. They figured out using LLM as an agent these days. And then they think, I have one agent. What if I had 20? What if I had 100? What if I had 100,000? So like bottom-up modeling is becoming very natural. So a lot of people care about like, how do I use LLMs as agents? So like you can do that also in our framework. Like you can have like 1 million LLMs to recreate a city and still run on a single GPU. And we have like algorithms to do that. But like a lot of people are coming in from that world. So a lot of the computer science people will find the bottom-up modeling come more naturally to them because they're already thinking like an agent that can interact with the rest of the world. And in terms of development, from an engineering point of view, absolutely. Like code development is super fast. That like all these AI tools can basically write good models. So if you have like the right architecture of the framework, the right abstraction, then like most software developers don't need to like write code from scratch. So it's possible you can write a model in like 10 minutes.
All right. So I'm going to thank you. Okay, can I throw one more at him real quick? So when you complete your PhD, what do you want to do? You're going to try and go into an econ department somewhere, or to a think tank, or to the government, or what's your plan?
I mean, I don't know. I mean, what do you advise? I mean, you've been through the cycle. I don't know yet. I still have to figure that out. Like, what's your advice?
What I tell our students who work with us to do economics and system dynamics, I tell them, if you want to go to an econ department, it's going to be tough.
Yeah,
because maybe a public policy department or something, or political science or but straight econ is hard. Or like you mentioned, the central bank, what in England or whatever is used. So it might be that sort of route, government. If you want to do economic modeling rather than physics or this sort of thing.
Or you could go work at a finance firm and make a whole lot of money and F all that academic stuff. Your choice.
I know which one I'd recommend, that it's
So
not the one that I did.
Yeah, right.
Yeah. So Steve, we'll do one more question here. Like, so he's a question about godly tables. So you can look at a godly table in two ways. You can look at it as a visualization tool, and there's many Python packages where you can visualize a table where you got your stocks as your columns and your flows as your rows. But Steve, define what a godly table is mathematically within Ravel-Minsky, what it's actually used for. What does it represent
Well, it's
mathematically?
basically the conservation of money, in a sense, because when you look at financial assets, a financial asset is a claim on somebody else. So each financial asset has a pair of financial liability, and the sum of the two is zero. Okay? And that gives you a conservation law about the sum of all financial assets and liabilities is zero. So it's a conservation law applied to financial transactions. And you would, if you have some of your agent interactions would be one agent buying something off another agent. So that'd be one of those points where the positive one is identical in magnitude to the negative for the other. So the conservation still applies. But what the godly table does, it puts that through the banking system. So it's a way of modeling the layers of the banking system. So you and I have our own personal balance sheet. We then bank at a bank, which has its balance sheet of its assets and liabilities, and we're part of that. And then you have the national level, and then at the international level as well. So the godly tables let you have that whole structured set of assets and liabilities. So yeah, I imagine you could do it fairly easily in your framework, because obviously every interaction which involves a purchase is going to have a positive one and a negative for the other.
I was hoping you'd just say you can visualize your ordinary differential equations in a table, but the long answer works.
That's the other thing. It
as
generates
well.
differential equations. That's what it's actually doing in the background. People are actually often, given how you obviously are completely fluent in ODEs and PDEs for that matter. Most economists really have very little training. They don't get much. If they do any, like if an undergraduate student won't even know what a differential equation is. If you get a student going to a post sort of master's or PhD level, they may learn second order linear differential equations. That's about as far as they go. There's no way they learn Stern-Weevil theorems or Feigenbaum numbers or anything of that nature. They just don't get into the full complexity that anybody who works in mathematics necessarily learns. So they're quite ignorant, frankly, on the area in which you're obviously an expert.
And Aish, thanks for spending 2 hours with us.
Yeah.
Thank you. Thanks a lot for having me.
It's 2 hours of your life you're never gonna get back, man.
Yeah, you won't get it back. And I often say, a lot of our guests come into the lion's den, and we can question you really hard. But I have to say, and I can speak for Mike and Steve too, like we see the value in agent-based modeling and moving that forward, because that's stuff we need in economics, whether it's system dynamics, agent-based, or some other novel technique that's not being used in the field right now. We strongly encourage it, and we strongly encourage work like you're doing yourself. In honor of Mike coming back to the show, I'm going to leave it off with a video that I haven't shown in a few years of him, and then close out the show. We will see you next week, same time, probably. I'll let you know on social media. Until then, enjoy the short video and see you next week.
I'd get Taylor Swift to endorse my hammer.
No! God, please, no! No!
I'd get Taylor Swift to endorse my hammer. Taylor Swift, Taylor Swift, Taylor Swift.
Taylor Swift.
To endorse my hammer. To endorse my hammer. To endorse my hammer.
Endorse my hammer.
Oh, I didn't even think of that. Come on now. Oh.
I didn't even think of that.